The next time you're walking down a jet bridge to board your flight, take a moment to look at the engine hanging off the wing. It looks like a massive, stationary cylinder of metal. But inside that casing is a machine capable of generating over 100,000 pounds of thrust. To put that in perspective, a single engine on a Boeing 777 has more horsepower than 28 Formula One cars combined. It is a machine that can inhale enough air to empty a professional football stadium in less than a minute. So how does this mechanical beast turn air and fuel into the raw power required to push a 200-ton airplane into the stratosphere? Jet engines can look intimidatingly complex, covered in thousands of wires, tubes, and sensors. But if you strip away the layers, the core principle is something you learned in middle school science class. It's Newton's third law of motion. For every action, there is an equal and opposite reaction. If you want to move forward, you have to push something backward. While a car pushes against the pavement with its tires, a jet engine pushes against the atmosphere. It's a continuous, high-speed cycle of air management that engineers often summarize in 4 simple words: suck, squeeze, bang, and blow. Unlike the engine in your car, which works in strokes or pulses, a jet engine is a continuous flow machine. Once it's started, it doesn't stop moving air until the pilot shuts it down at the gate. Every jet engine, from the smallest private jet to the largest wide-body hauler, follows the same fundamental thermodynamic cycle known as the Brayton cycle. Air goes in, gets compressed, mixed with fuel, ignited, and then blasted out the back. It's a refined, high-speed version of a controlled explosion that happens thousands of times a second. The journey begins at the front of the engine with the intake. In a modern, high-bypass turbofan, the kind you see on every Southwest or Delta flight, this starts with those massive, curved fan blades. These blades are masterpieces of material science, often made of titanium or carbon fiber. At cruise speed, these blades pull in massive quantities of air. However, the intake isn't just about grabbing air, it's about preparing it. The shape of the intake slows the air down slightly and stabilizes the flow so that the internal components of the engine don't get overwhelmed by the sheer velocity of the incoming wind. Once the air passes the fan, it enters the compressor. This is where the squeeze happens, and it is arguably the most brutal part of the process. Inside, rows of small, highly pitched blades spin at incredible speeds, forcing the air into an increasingly smaller space. Think of it like trying to pack an entire room's worth of air into a shoebox. By the time the air reaches the end of the compressor, its pressure has increased by up to 40 or 50 times that of the outside atmosphere. But there's a byproduct to this pressure: heat. The air becomes so compressed that its temperature can soar to over 1,000 degrees Fahrenheit before we even add a single drop of fuel. Now that we have incredibly hot, high-pressure air, it moves into the combustor, or the burner. This is the bang phase. Here, fuel is sprayed into the air in a fine mist and ignited. Because the air is already so hot and pressurized, the fuel burns with extreme efficiency and intensity. We aren't just talking about a campfire. We're talking about a sustained inferno that reaches temperatures of nearly 3,000 degrees Fahrenheit. This is actually hotter than the melting point of the metal blades inside the engine. Engineers prevent the engine from melting by using film cooling, bleeding a thin layer of relatively cooler air over the parts to act as a heat shield. The final stage is the exhaust. Those superheated, rapidly expanding gases want to escape, and they only have one way out: the back. But before they leave, they have to pay a quote-unquote toll. They pass through a series of blades called the turbine. The rushing gas spins the turbine, which is connected by a long shaft back to the front of the engine. This is how the engine stays alive. The fire in the back provides the power to spin the compressor and the fan in the front. Once the gas passes the turbine, it shoots out the exhaust nozzle at supersonic speeds. This high-velocity exit is what creates the thrust that propels the aircraft forward. To visualize this, think of a simple party balloon. When you blow it up, you're compressing air inside the rubber skin. As long as you hold the neck closed, the pressure is equal in all directions. But the moment you let go, the air rushes out of the opening. Because that air is moving backward with force, the balloon experiences an equal force pushing it forward. A jet engine is essentially a balloon that never runs out of air because it's constantly sucking more in at the front and adding energy, fire, in the middle to make the air come out even faster. Here's the secret that most passengers don't realize. In a modern jet engine, most of the air you see entering the front doesn't actually go through the fire part of the engine. This is called bypass air. On a modern Boeing 787 or Airbus A350, about 90% of the air pulled in by the giant front fan simply flows around the core of the engine and exits out the back. Only about 10% goes inside to be burned. It turns out that moving a large amount of air slowly is much more fuel efficient and quieter than moving a small amount of air extremely fast. The core of the engine is essentially just a giant gas generator used to spin that massive front fan, which acts like a highly advanced propeller. This is exactly why jet engines have become so enormous over the last 30 years. If you look at an old Boeing 707 from the 1960s, the engines look like thin pencils. Today, the engines on a GE9X powered 777X are as wide as the fuselage of a Boeing 737. Bigger engines mean bigger fans, and bigger fans mean we can move more bypass air. This makes the engine significantly quieter for people living near airports and drastically reduces the amount of fuel needed to cross the Atlantic. It's not just about more power, it's about more intelligent power. So, the next time you hear that low, rhythmic hum while cruising at 35,000 feet, remember that you aren't just listening to a machine. You are listening to a masterpiece of fluid dynamics. It's a system designed to manage air with surgical precision, sucking it in, squeezing it until it glows, and blasting it out to defy gravity itself. The jet engine didn't just shrink the world, it mastered the very molecules of the atmosphere to make the impossible possible. If you've ever looked at a plane and wondered, how? You're in the right place. From the chemistry of jet fuel to the secrets of supersonic flight, we break down the complex world of aviation so you can understand the why behind the how. Make sure to hit that subscribe button, turn on notifications, and join us for the next flight here on Aero Explained. Blue skies and tailwinds, everyone.